you worry that in any complicated experiment like this, that you may have made a discovery, but you're not sure that the discovery is really true. And I mean, there's many situations in my life where that's happened.
We've been through a whole series of exercises to figure out what this was, and many of them, underlying them, are self-doubt. We're like, could we have caused this by our own ignorance, or anything from accidents to, to malpractice?
There's this wonderful thing that goes around, is there some evil genius that has laid this into us? This evil genius gets to be more and more complicated and more skilled as you delve into this in a deeper and deeper way. So it's not just one evil genius, it's a multiple group of evil geniuses.
Every check we've done has kind of come back saying, no, this really came from some astrophysical origin, we believe. I mean, nothing in the instrument that we found so far could have done this, and nothing that we have found so far indicates that it could have been some intentional or accidental or malicious injection. And so then you start almost believing it. And that's pretty cool.
I think the remarkable thing is not so much that we saw a gravitational wave. I mean, that's remarkable enough, but it isn't the real centerpiece of this whole discovery. That centerpiece is the fact that we saw a particular source that nature seems to have given us. It's the best source we could have imagined. It's the source that says Einstein is right on every goddamn detail almost. In other words, this is a source that doesn't require any other physics than general relativity. Let's think of that.
So the story of LIGO is one that has been told multiple times on this campus, so I'll start on a more personal note. Because on September 14th, 2015, I was actually in bed with the worst fever I had had in years. But like the good Caltech student that I am, I kept frantically checking my email for fear of missing out. And that's when I caught this message with like the odd title of Very Interesting Event, which was telling us about a very interesting event that had supposedly showed up in LIGO data. So this was all enough that I immediately jumped to my computer, emailed Alan to see if there was anything I could do to help with this, and try to log into the Caltech computers and see if I could see the data and find out what this very interesting event was all about. But the fever got the best of me and I failed. And then I accidentally deleted the email, and in the days later when I was feeling better, I even thought it had all been just a weird fever dream. Except there had been also hundreds of other follow-up emails of people freaking out trying to make sense of what had happened on that day. And that is how I found out that the Earth had shaken on that day. The Earth found out a few months later when we announced the first direct detection of gravitational waves. And this was a phenomenon predicted by Einstein 100 years before, and it was a remarkable, monumental achievement, so much so that even the public got excited about it, and you can see some of the covers of newspapers around the world announcing our discovery. The public got excited even if they didn't really know what there was to be excited about, but something important had happened. So my first goal with this talk will be to elucidate some of the importance, explain why this was so remarkable, and then move on to tell you a little bit about what I do here at Caltech, trying to, as Alan tell you, measure some of the fundamental properties of gravitational waves. But before we do that, I'll ask you to take a step back and think about your most fundamental intuitions about how space and time work. If you're anything like me, to use time is perhaps some sort of clock that ticks regularly for everyone and everywhere. It doesn't matter who or where you are. And space is perhaps some sort of three-dimensional Cartesian grid on which we can locate events as that happen at a given moment in time. But 100 years of scientific development point us to a different picture, one in which actually space and time come together into a fabric of space-time which can curve in the presence of gravitational, of mass or energy. And this curvature is what we experience as the force of gravity. So space-time is not rigid. It can bend, it can squeeze, it can stretch. And it's no longer just a featureless stage on which the events, the history of the universe unfolds, but it's an active actor in this play. So space-time is dynamic. That's the fundamental message from Einstein's theory of general relativity. And the theory can be quite complicated. It's summarized in Einstein's field equations, but the main message is just that space-time tells matter how to move, and matter tells space-time how to curve, which was eminently boiled down by the famous physicist John Wheeler. So we're left with a picture like this, in which we can explain the gravitational interaction between two bodies, say the Sun and the Earth, as the result of the curved space around them, which here is represented by the two-dimensional green grid that bends around the two objects. But for our purposes, the most interesting part or lesson to be drawn from this picture is that if this is just a static snapshot of this system. The Earth and the Sun are orbiting around each other, and as they do, this configuration of matter changes, and so the curvature of space and time around it must respond to that. And it can only do so at a finite speed. That's another basic law of physics. Nothing can propagate faster than the speed of light. And when you have a perturbation that can only move at a finite speed, you get waves. And this is just like when you drop a pebble in a pond, or when you accelerate an electric charge and create ripples in an electromagnetic field, which is light. Except these waves are waves in the gravitational field, and there's a dual language that you can use to describe these things in terms of the curvature of space and time or gravitational fields, and I will use either, so don't get confused. If you get confused by the notion of curved space-time, just switch that in your head to gravity. So these gravitational waves are an actual physical effect, and as perturbations in the curvature of space and time, their effect is actually to literally stretch and squeeze distances. So you can imagine that a gravitational wave coming into the screen will at one moment stretch me in the vertical direction and squeeze me in the horizontal direction, making me taller and thinner, while the next moment, a period later, it will do the opposite and compress me vertically and expand me horizontally, making me fat and short. Another way to visualize that is that if you imagine you have a series of free-falling rings just out in space, and they form a cylinder, if there was a wave propagating in the direction of the axis of the cylinder, then it would compress and stretch the rings in this form, so you would see something like this. So the effect of a gravitational wave is to stretch or compress distances in a way that's proportional to the distance that you start with. So if you imagine just grabbing one of those rings that I was just showing you, the gravitational wave will come in at one moment, deform it so it gets stretched in one direction and squeezed in the other. And so if you started with a distance with a length that is L, say in this case the radius of the circle, and the gravitational wave would change that distance by an amount delta L, which will be proportional to the length that you started with. And so we can define this quantity, which gives you the amplitude of a given wave, which is the strain. So you'll hear me talking about the strain a lot in this talk. And that just tells you how powerful, how strong the wave is. A strong wave will change a meter stick by, say, 1 centimeter, whereas a weaker wave will change it only by 1 millimeter or something like that. And that quantity, the strain, is what tells us what the amplitude of the wave is. So far so good, but this begs the question, if basically any accelerated configuration of matter can produce these gravitational waves, and the effect is something so obvious as literally stretching and squeezing distances, why don't we see them? Where are these gravitational waves? And the answer is everywhere, except they're extremely mind-bogglingly small. And to understand that, perhaps you can go back to the Einstein's equations, and very naively, what they can tell you is that the curvature of space-time, so how much space-time is curved in a given region with some concentration of matter, is proportional to the stress that is caused by that density of energy and or matter in that region. But the proportionality constant is some extremely small number. So that tells you that you need to apply a lot of stress, a lot of force. You need a lot of energy even to curve spacetime by a small amount. So spacetime is very hard to bend. This is a very naive way of understanding why these gravitational waves will always be so weak. But to maybe get a better feeling of what this means, we can consider the canonical or preferred kind of system to our source of gravitational waves, which are binary systems. So it could be two ice skaters holding hands, or it could be the sun and the earth, it could be the sun and the moon, or two black holes going around each other, it doesn't matter. So if you know math and you go back to Einstein's equations, they will tell you that the strain or the amplitude of a gravitational wave will be inversely proportional to your distance from the source, which is to be expected. That's what happens with sound or with light or whatever wave. The amplitude will decay the farther away you are from the source. It will be directly proportional to the two masses of the objects that are orbiting around each other. And it will be inversely proportional to the distance between them. So the closer the two objects are, the faster they move and the more gravitational waves they emit. There's a slightly more complicated relationship for the power that is emitted by the gravitational waves, by the source. But the main message is that the more mass closer together, they move faster and will create more gravitational waves. So you can try to use these equations and plug in the numbers from some example system to get a feeling for what this actually means, and say that the Earth, again, the Sun and the Earth. For example, if I did the math correctly, which you should go and check because maybe I probably did it wrong, but in any case, you would probably find out that the strain, so the amplitude of a gravitational wave, 1 light year away from the solar system is 1 part in 10 to the 26. That means that distances will be changed by 1 part in 10 to the 26. And the total emitted power by the Sun-Earth system will be something that is equivalent to like 2 light bulbs. And that maybe doesn't seem so small, but you have to keep in mind that this is the whole mass of the Sun and the whole mass of the Earth behind this production mechanism creating these waves. And all they can do is just output a measly 2 light bulbs of power. Just for comparison, just the electromagnetic output, so the radiation in light from the Sun, is something like 10 to the 26 watts, which is like 1 septillion light bulbs. There aren't 1 septillion light bulbs here because I can only copy and paste so many light bulbs, okay? But the idea is, of this silly example, is that whatever the source is, gravitational waves will be very weak. And you will necessarily have to have an instrument that's extremely sensitive to be able to detect these very faint changes in distances as the waves go through the Earth. And that's where we come in. So LIGO is the Laser Interferometer Gravitational Wave Observatory. And it's an instrument designed to precisely detect the minute changes in length produced by these gravitational waves as they go through the Earth. As the name says, the key technology behind this instrument is interferometry. And so the idea is that you will grab a laser beam and split it into 2 so that it travels down 2 perpendicular arms, and each of the beams will then bounce back from a mirror at the end of the arms, and they will recombine at the center where they originally got split. If the 2 arms are precisely the same length, then the phases of the light will work out such that no light comes out from this side of the instrument. However, if there's some mismatch in the length of the 2 arms, some light will escape, and we'll be able to detect it with a photodiode, which we can then convert into an electric digital signal. And that way, when a gravitational wave comes in and changes the distance, the relative distance, there's a mismatch between the distance of the length of the 2 arms, we'll be able to see that and record that. Our actual instruments are quite a bit more complicated than this. To begin with, the arms are each 4 kilometers long, so 2.5 miles long. And what you see there are concrete tubes that protect, concrete enclosure that protects metal tubes that are kept at a vacuum of, I think, 10 to the -9 torr, which is 1/trillionth the pressure of the atmosphere. And that's so the infrared light that we use can travel back and forth almost without scattering. And I said instruments because there's 2. There's the one in the deserts of Hanford, Washington that you were just looking at, and there is a second twin instrument in the swamps of Louisiana, which you'll see in a second. The 2 instruments, the 2 facilities are designed to be precise clones to each other. And they share not only the very cutting edge technology to make the most stable laser probably in the world and extremely high vacuum, but also cutting-edge seismic isolation technologies, and in particular, the extremely precise, beautiful, perfect optics, the mirrors, which are polished to nanometer level, so basically atom by atom, so that they are as smooth as possible, and they have all sorts of optical coatings and a lot of technology that escapes me. But the idea is that these are some of the most perfect mirrors for the kind of infrared light that we use, and they will absorb only 1 out of something like 3 million photons that bounce off it. And they're around this size, and they're 40 kilograms each, so they're quite big. And these are placed at the end of the arms and in different intermediate parts. So this is an extremely complex machine with a lot of nuances that require the development of new technologies and a lot of work. It's not only extremely precise, but it's also implemented at a scale that is very large for this kind of precise measurements, which is very challenging. So it's not surprising that it takes a lot of people to make something like this work. And this is a more or less recent picture of the LIGO laboratory group here at Caltech. But overall, there are around 1,000 people in 8 institutions, 16 countries around the world, which contribute to the LIGO scientific collaboration, either by working on the instruments or the analysis of the data that they produce. So it is thanks to all these people that we were ready on September 14th, 2015, when the LIGO instruments detected the faint rumble of the first gravitational waves to ever be detected directly, I should say. And these gravitational waves originated at the very end of a cosmic dance that had lasted for millions of years as 2 black holes orbited each other, emitting gravitational waves and finally crashing and producing a fantastic burst of gravitational waves that was more powerful than all of the stars of all the galaxies in the whole visible universe combined. Luckily for us, we were quite far from such a cataclysmic event. The signal actually took 1.3 billion years to reach Earth. So when this signal was emitted, multicellular life was barely starting on the planet Earth. Then the dinosaurs came by, they went extinct 15,000 years ago. When the signal was on the outskirts of the Milky Way galaxy, Homo sapiens was just starting to take over the Neanderthals and stuff, and eventually 100 years ago, Einstein predicted these waves should exist, and then finally on September 14th, 2015, the waves passed through the Earth just little after we had turned on our events, our instruments, so we could actually detect it. All of this is not made up. We know it from the data that the instruments recorded. And so the instruments recorded actually around 1/5 of a second of signal, and from that we can reconstruct this whole story that I told you about. And because the instruments will dance to the beat of these long gone black holes, and in so doing they will record the signal using the photodiode. So it's an electric signal which we can store as a digital file, and then we can convert to a sound. It so happens that the frequencies of the signal fall well within the hearing range of humans. So I can actually play it for you if the gods of audiovisual work. So what I will show you now is the actual data recorded by our instruments. On the x-axis here, you see the time. So as time progresses, the signal goes through the Earth. And on the y-axis, there's the frequency of the signal, so the pitch. And then you'll see color traces, which will, or a color map, which will indicate how powerful, so how much energy there is in the signal at that given time and frequency. And of course, I should say the 2 panels correspond to the 2 instruments. Let's see if this works. You'll hear 2 versions of this sound, one which is more authentic and the second one which has been pushed higher in pitch so you can hear it better. This characteristic structure, which we call a chirp, because it's whooping up in frequency and amplitude. It's actually a direct consequence of the dynamics of the system that produced this signal. As the two black holes came closer together, they emitted more gravitational waves, which caused them to become closer even together, and that makes them go faster, and so they emit more gravitational waves, and that's a runaway process that ends up with them crashing into each other and emitting this whoop, this chirp of gravitational waves. So for you to have an idea of what this means, at this point of maximum amplitude of the signal, the strain that was associated with this gravitational wave, so if you remember the changing length over the length, was 10 to the negative 21. That means that our instruments that have 4-kilometer arms changed in length, the mismatching length between the two arms was 4 times 10 to the negative 18 meters. This is an extremely small number. So for you to get an idea, the width of a human hair is on average 10 to the negative 6 meters, I think. So 10,000 smaller than that, 10 to the negative 10 meters, is sort of the size of an atom. 10 to the negative 15 meters is the size of the nucleus of an atom. And so the mismatching length that we were able to measure was 1,000 times smaller than the size of the nucleus of an atom. So that's why it took 1,000 people and several decades to achieve the required level of precision to actually be able to measure this. Einstein himself, and probably most people throughout history, thought this would never be possible. This was only the first detection of many, actually. Since then, we've seen several other black hole systems merging around the universe. We named them very creatively with GW for gravitational wave, and then 15 for the year, 09 the month, and then the day that it was recorded. But perhaps more interesting even than, or different than these black hole system is the merger of two neutron stars, which we saw actually quite recently. Neutron stars are the dead cores of long-gone stars that eventually also crash just like the black holes we've been talking about. But being made of matter, they don't only emit gravitational waves, they also emit a whole plethora of electromagnetic emission across the spectrum. So radio waves, visible light, gamma rays, X-rays, you name it. And so this delivers an invaluable wealth of astrophysical information, and also about the nuclear matter that makes up these objects. So you can see already from all the stuff I've told you about that there's a lot of science going on here, and you can learn about the evolution of stars, about the history of galaxy evolution, clusters, even the history of the universe itself by doing cosmology with gravitational wave signals. These gravitational waves have opened a whole new way of doing astronomy and physics. And we have different teams, so there's different communities that focus on different aspects of all the science that we can do with this new information. But to me, perhaps the most exciting prospect is to use gravitational waves to learn about the nature of gravity itself. Gravitational waves provide a unique window into the nature of space and time, because they are a manifestation of the fundamental geometry of how space and time are woven together. I'm not the only one that finds this stuff the most interesting. The public tends to love this kind of stuff. And so then that leads to like very well-intentioned but awfully executed covers like this. The theory of relativity proved. This came out when we announced our first detection. We can't prove theories in science. You don't need to be Karl Popper to know that. We can only try to disprove theories. But nonetheless, we do try to learn more about fundamental physics from our observations. And we do that by comparing the predictions of Einstein's general theory of relativity, which has been exquisitely tested on many domains, but not necessarily gravitational waves. And we try to look at those predictions and look at our data and try to see if there's something new there. Is there a mismatch? Is there something that could point us to beyond Einstein physics? There are multiple ways to do this. You can compute precise waveforms, precise predictions for the structure of the signal that we should see and compare and see if there's any small deviation from that. Or you can look at fundamental properties of the wave, more basic things like their speed, or what I will tell you about, which is the gravitational wave polarizations. this is all totally biased. This is my interest, but I'm giving the talk, so today you'll hear about how to learn about gravitational waves polarizations. There are many interesting things you could do about fundamental physics with gravitational waves, but let's focus on this. Why? Because polarizations are a direct manifestation of the wave that of the fundamental geometry of space and time. And so to try to understand what this means, let us start with a light warm-up, thinking about electromagnetic waves. So light is a wave in the electric field. The electric field is a vector, so you can think of light as some arrow that oscillates up and down as the wave comes by. There are several ways in which a vector can oscillate. So one way is like vertically, like here, or it can do so horizontally. And these two different modes constitute what we call linear polarizations of the electromagnetic wave, linear polarizations of light. If you have polarized sunglasses, the way they work is by taking advantage of this fact and filtering out vertically or horizontally polarized light. Any kind of wave you can decompose into vertically or horizontally polarized modes, even if it's something like a circularly polarized electromagnetic wave. And so, because light is a vector and it has these two polarizations, at any given point of as the wave is propagating, at any given point in the electromagnetic field, you can restore the state if you rotate everything by 360 degrees. So if you look down as the wave propagates towards you, as light propagates towards you, at any given instant, the vector of the electric field will point in some direction. And if you freeze it and if you rotate it by 360 degrees, everything looks the same. So we say that these kinds of waves have spin weight 1 because it just means that they behave like a vector and they have this symmetry property. You could imagine that a different way in which light could work could be that the oscillation of the electric field happened not transversely to the direction of propagation, but longitudinally. And so in that case, if you looked into the direction of propagation, then you wouldn't see this. You wouldn't have to rotate by 360 degrees. You could just, any angle that you rotated by, it would look the same. And that would be what we call a spin zero or scalar polarization. But the laws of physics preclude that. Maxwell's equations don't allow you to do that. And so in reality, light only has these two transverse components. But if we didn't know that Maxwell's equation said that, if we didn't know in the quantum language, for those in the know that photons have mass, we could experimentally check that and try to see if what is the geometry of the polarizations of light. And that is going to be what we want to do, but with gravitational waves. In the case of gravitational waves, it's a little more complicated. You don't only have 3 options, 2 of which are allowed by the theory. You have 6 options. And so I will try to break this down for you, but they are the 6 options for how space can be stretched and squeezed as the gravitational wave whizzes by, are represented here by their effect on free-falling rings of particles, like I showed earlier. So the effect that I showed you before is this one, in which the gravitational wave stretches and squeezes the ring in perpendicular directions transverse to the direction of propagation. But let's start with these 2. So these 2 modes we call scalar modes, because what they do is, first one, the breathing one, will grab space and it will stretch it and squeeze it in a plane that's perpendicular to the direction of propagation, here always indicated by the arrow, and it will do so symmetrically around the axis. Then the longitudinal mode will just stretch and squeeze along the direction of propagation. So for these 2 modes, if you looked in from above, it will look symmetric to you at any given time around the direction of propagation. So we say again that these modes have spin weight 0, that we call them scalar modes because of this symmetry. It's just a label. You could also have what we call vector modes, in which the stretching and squeezing of space happens partially along the direction of propagation and partially along the x or y axis. And for these 2 modes, if you look down from the direction of propagation, in this case, if the waves come in this way and I look towards this in this direction, then what you would see is just, well, you can imagine an arrow, a red arrow pointing down and a green arrow pointing down. It just looks like a single arrow, just like in the case of electromagnetic waves that I showed you first. And so if you rotate it around 360 degrees around that line, you recover the state that you were in. And so this has the same symmetry as light, and we call these vector polarizations. Finally, you could have the stretching and squeezing happen only in the plane transverse to direction of propagation, and that could be, and that would be in two perpendicular directions. That could be if they are like this, or they could be 45 degrees rotated from that around the direction of propagation, and we have these two modes which we call plus and cross. And these two polarizations we call tensor polarizations, because if you look down the direction of propagation, their symmetry is such that you don't have to rotate it by 360 degrees to recover what you had originally. You only need to do so by 180 degrees. So we say they have spin weight 2. So again, all these polarizations are allowed just by generic geometric arguments. So it's just like how many different ways you can deform space with respect to the direction of propagation that a wave is propagating. As it turns out, GR categorically only allows these tensor modes for deep reasons having to do with what GR says the properties of gravity should be of the structure of space and time. But there's a whole slew of theories out there that have different predictions, and you can see that which polarizations are allowed by different theories. It doesn't matter the details, it's just for you to have an idea that if you want to go beyond general relativity, you usually can't avoid, or it's a very common feature that you will have to add some degrees of freedom that will show up like extra polarizations. The message is that if you see that the gravitational waves have any, say, longitudinal component or something that's not the plus and cross polarizations that GR predicts, that's a total no-go test for GR. And it's directly pointing you to something new that we don't know about. But forget about the theories for now. What we actually want to do is to be able to measure this. And so how can we do this? Well, our instruments take this differential. The only thing that our instruments measure is the mismatch in the length between the two arms. So if a gravitational wave of some given polarization, say a plus polarization with the axis of stretching and squeezing aligned with the arms, comes in right from above, this differential change in length would be maximal. And so the interferometer will measure this gravitational wave very well. However, if the same wave came from a different direction, say with the direction aligned diagonally along the diagonal of the arms, it will stretch and squeeze the two arms at the same time so that there's no mismatch at any given moment, and so the instrument cannot measure anything. So this gravitational wave could be going by and we wouldn't see it at all. We can represent this angular dependence of the sensitivity by looking at a plot like this, in which you should imagine that you place a detector at the center with the vertex at the origin, and so these are the two arms of the detector. And in any given location, let's say you have a source here with respect to the detector, the radial coordinate will tell you how sensitive you are to a gravitational wave of this given polarization coming from that direction. So if it's over there, this arrow is very long, so it means that our response to that signal is very good, so we can measure it very well. If it came, for example, from the side instead, we don't actually have any sensitivity to that location in the sky, so that's bad. And the key point is that this angular sensitivity is very different for each polarization. So for maybe I am very sensitive to a plus polarization coming from here, but if it was a scalar polarization, I shouldn't be able to see it. And this is what is going to allow us to discriminate between the different polarizations given the data that we've seen. The easiest way that you could imagine doing this is if you had a continuous signal coming from a given location in the sky. If you had that, so let's say it's just a monotone, like boo, and then it's just, it's coming from there in the sky. As the Earth rotates, the instrument will move with respect to this source the source location, that point in the sky. And so as seen from the detector, actually the source is moving with respect to the detector in the detector frame. And so the sensitivity to that source will go up and down as the source, as that point in the sky traces an arc around as the Earth spins on its axis. And so you see the arrow here would represent the sensitivity to a given point in the sky as the Earth is rotating. So to the detector, it looks like the source is moving. And so your sensitivity goes up and down as the Earth comes in and out of the most sensitive regions for you. And this would be totally different for the different polarizations. And so the way this would manifest itself in your data is that you would see a signal that if intrinsically has the same amplitude, but you record it with growing and decreasing amplitude depending on the polarization it has. So there's an intrinsic amplitude modulation associated to any polarization at any given point in the sky. And this is what I'm showing you as an example for a given point in the sky. For a given detector, you can predict how your sensitivity should evolve as a function of time with a period of a day. So it will repeat itself once the Earth comes back to where it was. So these are what we call continuous signals. They're a subset of, I guess, persistent signals, which would also include stochastic backgrounds, which I won't discuss in this talk, but they are sort of like the cosmic microwave background, but in gravitational waves, for those of you who know. But the point is that if you have a signal that lasts very long, this amplitude, this characteristic amplitude pattern will get imprinted on the signal, and it will be a key feature that will allow us to tell which polarization the signal has. Luckily for us, we know that there should be sources that exactly give us something just like what I described before, a monotone from a given particular sky location. This is because,
Little wonder.
Oh.
If we expand.
All right, let's skip that. This is because when a star dies, it will, as I mentioned before, if it has exactly the right mass, its core will contract, and if it's not too heavy, it will not form a black hole, it will instead form a neutron star. And that's what I wanted to show you, but okay. Let's not do that. The neutron star is it has around a couple times the mass of the sun in the size of Pasadena. And it's almost a perfect sphere, but it's possible that it has a slight asymmetry, a small mountain that might be even a centimeter high or something small like that. And it's spinning so rapidly that even such a small asymmetry would create, it would be enough, a source of gravitational waves that are strong enough that we may be able to see. And because this is not, it's almost not slowing down, it's slowing down a little bit, but because of that, the frequency of the gravitational wave will be almost precisely constant. And we know exactly where the source is because we can see this neutron star spinning in the sky, and we can target our searches and see if there's a signal, a gravitational wave signal coming from these asymmetric neutron stars. The cool part is that you have to also know the way we search for these signals. We assume that we know the polarization that the signal has. So we assume that Einstein is correct, and we say, well, given the source and sky location, we should see this sort of signal in the data, and we try and look for that. So if you assume the wrong sky location, let me show you the animation that I have.
Scott.
How does that work? Okay. If we assume the wrong sky location, the wrong polarization, then you would actually not see the signal. So what we did is we went back to the data and we said, well, maybe Einstein has been wrong this whole time, and the polarization of these signals is not like he predicted. It's not the transverse plus and cross signals, but it's something, polarizations, but it's something different, in which case there could be a very loud continuous wave from one of these pulses that we know exists, but it would be hiding in the data because we assumed the wrong polarization. We didn't find any signals, or we would have won another Nobel Prize by now and you would have heard about it. But we still were able to place the first upper limits for this non-tensorial, non-GR emission from 200 pulsars that we know are there, and so we try to make sure that there are any continuous wave signals of any polarization. It could be vector, and so what you're seeing in this plot is the maximum amplitude that a signal from any given pulsar indicated by a dot, the maximum amplitude it could have so that it's still hiding under the data and we didn't see it, and under the noise and we didn't see it. And this is the gravitational wave frequency of the signal we expect for each of the pulsars. This is one famous pulsar, which the movie was about, but it didn't cooperate, the Crab pulsar, which we target among all of these. So we have the first vector upper limits, so the first limits of how much non-GR signals these pulsars could be emitting, and also the first scalar upper limits as well. But anyways, this will be a great resource once we actually detect one of these signals, because we'll be able to, even with one detector, measure and say exactly what the polarization of the signal is, even to a very precise level. But how about the signals we have seen? These are very, very different, actually. They're not long, they're very short, and so we can't actually do this. We can't play with the rotation of the Earth and try to see the amplitude modulation and try to identify the polarizations that way, because these signals last at maximum some seconds, whereas we need something that lasts at least a whole day to see the modulation, as I explained. But instead, what we can do is, if you have several detectors around the Earth and you have a gravitational wave of some given polarization that's coming in from some sky location, it will go through the Earth and it will interact with the different detectors, and it will ring them up differently just because the relative orientations is different. So some of the detectors will respond more or less than the others, just depending on how they were oriented with respect to the gravitational wave and how and what the polarization of the wave was, so what the geometry of the wave itself was. So we can grab these relative amplitudes and delays between the signals at different detectors, and we can try to reconstruct both the sky location, so where the signal came from. This is sort of what you do with microphones. Microphones can't really say where a sound signal is coming from. You have to use at least 3 microphones to triangulate where a given sound is originating. Same with your ears. The way you know where someone calls your name, the way you know where it is by actually shaking your head a little bit and noticing the difference between your 2 ears. Your brain does that for you. And so our instruments work sort of the same way. You have to triangulate to reconstruct where the signal is coming from. And there's also in there the polarization of the wave. So if you want to know with certainty where the signal came from, you would also need to include some assumption about what the geometry of the wave is. So the relative amplitudes and phases and the time delays between the signals at different detectors can tell you where the signal is coming from and what polarization content it has. This is for our first signal. So this orange area marks where we think is the most likely region in the sky that the source was located at. And that was obtained, we only had 2 detectors, and that was obtained assuming the polarizations were just as Einstein predicted. If you had assumed that they were totally not like Einstein predicted, so instead of being tensor modes, they were vector modes, it would still work, the analysis would still work, but you would infer a different sky location for the source. And so there are some degeneracies here between the different polarizations and the sky location of the source and the different relative amplitudes, phases, and delays that they would produce in a network. So ideally, we would need 5 detectors at least to try to break these degeneracies and disentangle the full polarization content of a given signal as we see it. It's 5 polarizations because I started with 6, but actually the 2 scalar modes are indistinguishable to us, so there's actually 5 polarizations that we can distinguish, and so those 5 unknowns, so you need at least 5 detectors to uniquely determine what the polarization content of a signal was. But if you don't have 5 detectors, let's say you have 3, in that case you can start to make some partial statements about what the polarization content of the signal should be. And so we do have 3 detectors, luckily. That's why I said that. We have the 2 LIGO detectors and our sister experiment in Italy, Virgo, which is a very similar, also an interferometer. It has 3 kilometer long arms instead of 4 kilometer long arms, but we all work together. And so if you see a signal with 3 interferometers, you can start to discard some models. So for example, for our first detection, it could have been that that signal we saw was produced by a fully non-GR polarization wave. But with Virgo, now we were able to use one of the later black holes that we saw. This one was the first one that we saw with 3 detectors, so it happened in August 14 of last year. You can actually try to see whether some of the hypotheses are disfavored. And if you look at the data, you will find that in this case, the GR prediction that the polarization should be transverse plus and cross like Einstein predicted is 300 times more likely than it being vector with the longitudinal geometry that I showed you earlier. And if you do that to compare tensor versus scalar, you find it's 1,000 times more likely. What this means is that the data, it's hard to explain the data as well if you want it to be a longitudinal wave, or it has some weird geometry totally different from what Einstein predicted. And this was really the first handle that we got experimentally on gravitational wave polarizations, as measured here at Earth, just without assuming anything really about, or almost anything about the source, and trying to measure from the geometry of our instruments, infer what the geometry of the polarizations of the wave were. Because there's some degeneracy between polarizations and sky location, if you're paying attention, you should be wondering, what can we do, or can we say using the data from our binary neutron star detection? Because in that case, we saw exactly where it happened, so we know where it came from a priori. And so we should be able to do much better at telling what the polarizations of the wave were. I'm not allowed to say anything about this yet because it hasn't been published, and if I do, some LIGO sniper will kill me. But because I know you're dying to know, I can tell you what you should expect. And what you should expect is that we indeed do very well. And I'll show you why. So we can grab those 3D plots that I showed you earlier for the sensitivity of a given detector for a given angle and polarization, and we can make it into a heat map. So in this case, each of these plots, for example, this one tells me that Livingston should be very sensitive to tensor signals coming from this location in the sky, but not so sensitive from signals coming from this location in the sky. And so there's a characteristic pattern for each instrument and each polarization. And so, for example, we know that the binary neutron star happened in this location in the sky. And so we should expect that the Hanford detector should have seen it very, very strongly, very well. So it should have recorded the signal without problem. So same thing for Livingston, the 2 LIGO detectors. So they should have responded a lot to this signal. But the Virgo detector, the Italian detector, shouldn't have seen much if this was indeed a tensor wave like Einstein predicted. If this wasn't a tensor wave, if it was a vector wave, for example, the story changes, and you shouldn't see too much power in Hanford. You should see some power in Livingston and a lot of power in Virgo. So you can look at the data and see if you actually saw the signal very strongly here in Virgo, then you can say that doesn't agree with what Einstein said should happen. And that's a similar story for scalar as well. So this is the way we can start to distinguishing between these hypotheses. So stay tuned for, for these numbers. Anyways, so with the recent detections of gravitational waves with our 3 detectors, we have for the first time learned about gravitational wave polarization geometry directly. And we found that, as expected, the models that agree with Einstein's predictions are favored from those that deviate from it. This is not a surprise. We expected this, but nonetheless, we hadn't actually been able to check that, not with 2 detectors. In the future, there's many more things we would like to do, like try to check if this signal is, for example, it's mostly like Einstein predicted, but has a small component that's a non-GR contribution to its signal. That's not something we can do right now because we don't have enough detectors to actually break all these degeneracies. Alternatively, if we detected a continuous wave signal, we would be able to do that as well and try to distinguish whether combinations of polarizations better. And that's very interesting to theorists. But nonetheless, this was a first baby step into measuring this new fundamental property that tells us about the structure of space and time pretty much directly. So there's a lot of science that can be done. As I told you, I just mentioned the very small, narrow area that I'm most interested in and that I've worked on the most. But there's a lot more, and I encourage you to go out there and learn about it. Currently, our detectors are down for improvements, and I think they will be up in December, if that's correct, for a third observation run of the advanced detectors. And our range would be much higher, so it means we'll be able to see signals further away. And so even though all of this stuff which I've told you about, which just sounds spectacular to you because it's totally new, it's a total new way of doing astronomy and doing basic physics, as impressive as it might sound, it will soon be dwarfed by all the new information that we gained from the universe using gravitational or advanced gravitational wave detectors. So it's a very exciting time to be involved in gravitational waves, so we're very lucky. And I look forward to what the future brings. Thank you.
Thank you very much, Max. Are there questions? Yeah.
Several parts. What's the theoretical maximum mass for a neutron star? And second, where is the boundary to then the minimum mass of a black hole that there is? And is there any evidence in terms of the masses that's revealing anything new?
I believe the maximum mass for a neutron star from standard physics should be around 3 solar masses, or like very extreme. There's no minimum mass for a black hole in standard physics, but to do that you would have to do quantum gravity stuff like I would, like I used to do. And from quantum effects you might get a minimum mass of sort of maybe the Planck mass, if you know what that is. But in classical theories there's no limit. There was another question.
Yeah, you mentioned multiple times about frequency of gravitational waves. So in case of electromagnetic waves, there is like simple relation between energy of say photon and then frequency. And in case of gravitational wave, is there a simple like first how to think about the frequency of gravitational wave, and is there a simple relation between energy of simple graviton versus
Yeah, same relationship. I mean, this is all classical, right? So I'm not seeing individual gravitons. We're seeing large amounts of coherent gravitational waves, so it's a classical thing. You can compute how many gravitons are associated with these waves that we have seen by using that formula you just mentioned. Yeah, same thing. Well, we don't know that. If you just expand. If you do a naive treatment of quantum gravity in the semi-classical limit, it should give you something like that. Yeah? Or I don't really see you, but.
Can you say anything about the medium through which the waves propagate?
Yeah, there isn't one. It's the space-time itself, and if you describe it in terms of curvature of space and time, the space-time itself, or space, if you just want to think about space, is endowed with the degrees of freedom, if you wish, in a sense, which carry this gravitational wave. If you want to just think about it classically, it would be the gravitational field. So this is like a wave in the gravitational field instead of the electromagnetic. Yeah.
Sorry, that's not what I meant. What I meant was, is the wave getting distorted as it moves through large?
That was a better question. Okay. Yeah, very, very, very weakly. You can compute that the interaction with matter, it's very, very small. And so for all intents and purposes, this is just geometrical optics for the waves. And that's the reason why it's so hard. They're so hard to detect as well, right? Yeah.
Yeah. So you have this slide stating that based on the data that you already have, the sort of tensor polarization modes are favored over the other two by like anywhere from 300 to 1,000 times when to, I guess, like, you know, Bayesian multipliers. Could you go into a little bit more detail as to how that's calculated?
Yeah, of course. So yeah, that's a statement about Bayesian odds. So we can look at the data. We have some priors. We can do math and integrate, and we get an evidence. So it's the probability that these data were produced, assuming it was either a tensor wave or a vector wave or whatever. And then you can compare the two, and you find those numbers. You find that one is 300 times larger than the other, or 1,000 times larger than the other. So these are odds in a Bayesian sense. If you change your priors, it would slightly change. But in this case, this preference doesn't come only from the priors. I don't think this is detailed in our papers, but I can tell you that if you just looked at how the waveforms match, so just an RMS goodness of fit measure, you would also find that the maximum likelihood estimator favors GR over the others. So it's not dominated by our priors. Good question.
Dr. Michio Kaku, here's a piece of video of you on this network in 1979.
If you look at the recent government reports concerning the 3 Mile Island, the government now concedes that 1 to 10 people will eventually die of cancer in the 3 Mile Island area.
Do you remember that time many, many years, almost 40 years ago, and what have you changed in your thinking since then?
Well, yes, I remember that very vividly because, you see, I'm a theoretical physicist, and I work with the theories of Einstein and the quantum theory. And so to be before a television camera is a new experience. But when the 3 Mile Island accident happened, all the media was saying, we need a scientist. We need a scientist who can help to decipher this mess to the American people. So they contacted me. And so I said to myself, well, this is what I do for a living. I'm a physicist. And so I said to myself, okay, I'll get on national television, get on national radio, because the situation demands it. Not because I wanted to do it, but because people had to know the dangers, the positives, the negatives of energy, one of the big questions of the age. And that's sort of how I backed into becoming a media person.
You say in your book that there was a teacher when you were in the 2nd grade that had an impact on you. Do you remember it?
I'll never forget. She walked in the room one day and said, God so loved the earth that he put the earth just right from the sun. Not too close, because the oceans will boil. Not too far, because the oceans will freeze, but just right from the sun. Now, I was floored. I mean, I was in 2nd grade. And here was a scientific principle with a religious interpretation. I said to myself, my God, that's right. If we were too close, the oceans would boil. If we were too far, the oceans would freeze. We are in the so-called Goldilocks zone of the sun. Now, of course, we have seen 4,000 planets orbiting other stars, and almost all of them are too close or too far from the sun. So you have 2 points of view. Either God exists, and God so loves the earth that he put the earth just right from the sun, or we have a crapshoot.
What do you think?
Well, now that we have found so many planets, 4,000 of them, we think that in the galaxy, our own backyard, there are billions upon billions of planets. On average, every single star you see at night has a planet going around it. Every single star on average. That it's indisputable that most of them are outside the Goldilocks zone. So you can still believe in God, but that's not an argument that clinches the deal.
So I want to ask you about a bunch of obvious things that you write about and get you to define it for a generalist. What is a planet?
Well, a planet is a mud ball that goes around a star. And I say mud ball because it doesn't release light of its own. It's dark. And it orbits around the sun, gaining energy. And we think that planets are very interesting because they could have life, because that's how we got started. And even in our solar system, we think that the planets may in fact harbor some form of life, maybe microbial life. And so we look at planets. We look at stars to find out where the planets are, but we focus on the planets because that perhaps is the habitat for life in the universe.
What's a star?
Well, a star is a gigantic solar furnace. It's a ball of hydrogen gas that releases energy by converting hydrogen into sunlight. And so a star is, in some sense, a gigantic hydrogen bomb. It obeys the same equations of Einstein, E equals mc squared, where m is hydrogen, E is sunlight that comes out of the star.
What is a comet?
Well, a comet is a piece of ice. It's like a dirty ice ball that whizzes around in the solar system. They're only like 10, 20 miles across. They're not very big, but they're basically made out of ice, remnants of the original solar system, which we think once upon a time surrounded the sun, but now orbit in a disk.
What's the difference between a meteor and a meteorite?
Well, that flash of light that you see whizzing across the sky is caused by a rock that burns up in the atmosphere, and that's called a meteor. Either the rock itself or the streak of light. However, once it hits the ground, it becomes a mineral, so we call it a meteorite. So a meteorite is a meteor which has fallen from the sky.
What's a galaxy?
A galaxy consists of hundreds of billions of stars left over from the creation of the universe, the Big Bang. They look like a gigantic disk, a huge simmering disk of stars. Our galaxy, for example, is the Milky Way galaxy, and the nearest galaxy to us is the Andromeda galaxy. And we think there are about 100 billion galaxies in the visible universe. So believe it or not, that means we can actually count the number of stars in the visible universe. 100 billion galaxies, 100 billion stars per galaxy, and so that's the number of stars in the visible universe, 100 billion times 100 billion.
What's an asteroid?
An asteroid is a leftover from the creation of the solar system. We're talking about debris that extends from the Earth, extends from Mars out to Jupiter, and we think it's a failed planet, a planet between Mars and Jupiter that never quite condensed or maybe got too close to Jupiter and got broken up.
So if you had to pick another place to live outside of the Earth, where would you go?
I would go to another planet. Now, we've looked at all the planets so far. None of them are exactly Earth-like. Venus, we once thought was tropical. Many science fiction stories have astronauts sunbathing on the beaches of Venus. We now know that Venus is our evil twin. Just like the Earth, closer to the sun, but temperatures are 900 degrees Fahrenheit. That's above the melting point of lead and tin. If you were to walk on the surface of Venus, your feet would sink into molten metals. So you don't want to go to Venus. Mars is the closest. It's a rocky planet. It's a frozen desert, but it's the closest planet we have to the Earth. But further out, the moons of Saturn and Jupiter look very interesting. One of the moons of Jupiter is Europa. It has a liquid ocean underneath the ice cover. Who would have thought that you could have a liquid ocean whose volume is larger than the oceans of the Earth going around that distant planet called Jupiter? NASA at some point wants to put a submarine under the ice to look for life forms under the ice cover.
We talked about your second grade teacher. Do you remember, well, obviously you must, when you first got interested in science?
I remember that very distinctly. I was 8 years old. Everyone was talking about the fact that a great scientist had just died. And I'll never forget, they flashed a picture of his desk on the newspapers, and the caption said something like this: "This is the unfinished manuscript from the greatest scientist of our time." So I was 8 years old. I said to myself, why couldn't he finish it? What's so hard that the greatest scientist couldn't finish it? It was a homework assignment, right? Why didn't he ask his mother? What could be so hard that you cannot answer it? I went to the library and I found out his name was Albert Einstein. That book was The Unified Field Theory, the theory that would allow us to, quote, read the mind of God. So I said to myself, whoa, that's for me. I want to be part of this grand expedition to finish that book. Now today I can read that book. I can actually see all the dead ends that Einstein pursued, and we actually think we have it. It's called string theory. I'm one of the founders of the subject, co-founder of string field theory, and we think we can actually complete that book that Einstein set into motion, The Theory of Everything. There's even a Oscar-winning movie called The Theory of Everything.
Go back your childhood. Where were you born? And what were your parents doing at the time?
Well, my grandparents came to this country about 100 years ago from Japan. And my grandfather was actually part of the cleanup operation in San Francisco after the San Francisco earthquake. So my family has a long history in California. But in 1942, because they were Japanese Americans, they were locked up at Tule Lake, a relocation camp, for 4 years. Behind machine gun and barbed wire, by the way. In 1946, they finally got out, but they were penniless. And we settled in Palo Alto, which is now ground zero for Silicon Valley. But back then, it was all apple orchards and alfalfa fields. And that's where I grew up, basically in a farm-like environment in what is now called Silicon Valley.
What did your parents do after they got out of the camp?
There was nothing for them to do except menial jobs. Their money was confiscated. They were broke. However, there was a certain cachet to being a Japanese gardener. So my father became a rather successful gardener, and he wanted me to take over the business. I tried gardening for a while, and after that I said, no way. I got to find another way to make a living. So when I was in high school, I decided I got to do something. So I went to my mom and I said, Mom, can I have permission to build an atom smasher in the garage? A 2.3 million electron volt betatron particle accelerator. And my mom kind of stared at me and said, sure, why not? And don't forget to take out the garbage. So I took out the garbage. I got 400 pounds of transformer steel, 22 miles of copper wire, and I built a betatron atom smasher in my mom's garage. I blew out every single circuit breaker in the house every time I turned it on. My poor mother must have said to herself, why couldn't I have a son who plays basketball? Maybe if I buy him a baseball. And for God's sake, why can't he find a nice Japanese girlfriend? Why does he have to build these machines in the garage? But that was a turning point. Because of the science fair projects that I did in high school, I earned the attention of an atomic scientist, Edward Teller. And Edward Teller pretty much took me under his wing, arranged for me to get a scholarship to Harvard. He knew exactly what I was doing. I didn't have to explain to him what antimatter was, what an accelerator was, what a betatron was. He knew immediately. And so he arranged for me to get a scholarship, and that started my life as a physicist.
How did you meet him?
Well, he came to Albuquerque, New Mexico for the National Science Fair. People don't know that, but he was in the habit of recruiting young scientists. He went to the National Science Fair where I met him. I was actually on television with him in 1963 in Albuquerque at the National Science Fair. Now, when I graduated from Harvard, he interviewed me for a graduate fellowship. But at that point, he was very clear. He said, look, I'm looking for people who want to design warheads, hydrogen warheads. Your physics would be very valuable designing newer and better hydrogen warheads. He offered me a scholarship. He said, Los Alamos, Livermore, MIT, you name it, we can arrange for you to work there. But you know, my interest then began to veer off in the direction of when I was a child, wondering what was Einstein's unfinished theory. You see, I wanted to work on an explosion bigger than a hydrogen bomb. I wanted to work on the Big Bang, the creation of the universe itself. And for me, a hydrogen bomb was just a footnote. I wanted to work on the creation of the universe.
Here's Edward Teller. This video goes back to 1974.
One of the decisive events which convinced me to work on nuclear weapons was a speech by President Roosevelt the day after Hitler invaded the lowlands, where he said, "It is the duty of the scientist to contribute the weapons which are needed for the defense of freedom.
Do you agree?
Well, that's a point that he stressed to me directly. He said, look, I'm recruiting. I'm recruiting for what the New York Times later called the Star Wars Scholarship. This scholarship propelled the brightest young minds in America from high school and college into Los Alamos to create the Star Wars program. Now, we know it had a checkered history. Many of the early designs did not work, in fact, for the Star Wars program. But that was the vision he had. He already had a very clear mission that science should be used in the interest of national security. You see, those times were different from today. We had the Sputnik moment. In 1957, when Sputnik went up, it was practically your patriotic duty to use science in the interest of America, because the Russians will one day orbit hydrogen bombs, not just Sputnik, but hydrogen bombs will orbit the Earth, and the homeland will be endangered. So that's why a whole generation of young kids became scientists and engineers and technicians, because it was the so-called Sputnik moment.
So when you were growing up, when did you discover that you had the brain to understand this stuff?
Well, when I was a kid, I read about Einstein, and my favorite quote from Einstein was, if a theory cannot be explained to a child, then the theory is probably worthless. Meaning that every great theory has a picture behind it that children can understand. Newton talked about, things moving in space, friction, the motion of bodies. Einstein talked about clocks and meter sticks and rocket ships, things that children can understand. And yeah, there are books trying to explain space-time to children. And I said to myself, wow, if the great ideas are all based on pictures, and you understand those pictures, then mathematics is bookkeeping. It's complicated bookkeeping. You have to learn how to do the bookkeeping, of course, but it's bookkeeping. It's the physical principle, the concept that makes everything move. Now, when Einstein was 16, he found that principle. When he was 16 years old, he asked himself a question: can you outrace a light beam? Now, we would say, well, that's a stupid question. I mean, outrace a light beam? What are you talking about? It took him 10 years from the age of 16 to 26, and he finally found the answer, and he changed world history. He found out that you cannot outrace a light beam. That's a children's question. And I said to myself, I can understand these children's questions. I just have to, of course, at some point learn the mathematics. But it's the principle that's involved. And today we know, of course, the speed of light is the ultimate velocity in the universe. Einstein is the cop on the block. And he figured that out starting at the age of 16. So all great theories have a physical principle behind it that children can visualize.
Yeah, but go back to as you went through that process, what were the milestones where you began to gather the knowledge and you had people that said, if you want to do this, you got to go here? Who else had an impact on you?
Well, to be very frank, a lot of people tried to give me advice when I was in high school, but I knew that most of the advice was wrong. You see, I tell kids today that you have to have a role model because the wheel's been invented already. Why do you have to reinvent the wheel if you want to become a sports figure or a movie star? The wheel's been invented. Find somebody you admire. Look at their life history. Follow the path. So I said to myself, I want to become a physicist, a theoretical physicist. I read about Einstein's life, so I knew exactly what I had to do at what age in my life. When do I have to get a PhD? When do I have to become a professor? When do I have to start to work on some big physical concept? It was no mystery to me. And so many young kids come up to me because they get bum advice from their high school teacher who simply wants them to go to trade school or learn something that is a little bit better than pumping gas. So I said to myself, tell the kids, find a role model. The wheel's been invented already.
So was Teller your role model?
No, it was Einstein, because Teller made a very big pitch for me to design weapons. And for me, at that point in my life, I realized that it's engineering. The basic physics of hydrogen warheads is well known, well established. As you know, China and developing nations got the hydrogen bomb practically in the first try. And so it was an engineering problem. I'm a physicist. I wanted to look at the physical concept of new, undiscovered things, like why did the Big Bang take place? What was the energy source of the Big Bang? Why did it bang to begin with? These are questions of cosmic importance that are far beyond the engineering of simply assembling a hydrogen warhead.
But again, why were you able to figure it out and most people are drowning all this language and everything when they would be back in high school?
Well, I think, unfortunately, we have a high school system that stresses memorization, stresses drudgery, and does not encourage the bright students to come up. For example, in Asia, they have the expression, the nail that sticks out gets hammered down. So if you're the oddball, if you're Steve Jobs, if you're Bill Gates, you get hammered down. But in America, we have the expression, the squeaky wheel gets the grease. Now, I was the squeaky wheel. I wanted to get the attention of my teachers in high school. That's why I built the Atom Smasher. As I found out, most of my teachers couldn't help me. But I wanted to do it because I said to myself, this is something that is doable. I just have to get the basic equipment, the basic physics I understood. And so it was not such a big deal for me to build an Atom Smasher.
What'd you do with it?
Well, I turned it on. Well, the goal was to create antimatter. That was the whole thrust of the Science Fair project. I photographed antimatter. Antimatter comes naturally from a radioactive source called sodium-22. I put that in a cloud chamber, put it in a magnetic field of 600 Gauss, and the beautiful tracks of anti-electrons bent in the wrong direction. Electrons bend this way. Antimatter bends the opposite way in a magnetic field. And I took beautiful pictures, cloud chamber pictures, pictures that are research quality, in fact, they tell me. And I won grand prize at the National Science Fair. And so I'll never regret doing a science fair experiment because that took me from a gardener's kid to getting a scholarship to Harvard and then beginning to work on the unified field theory. That's how it started.
What did the rest of the kids think of you?
Well, they thought I was nuts, of course. The teachers that I had to work with, I simply told them that I had to cut transformer steel, I have to glue copper wire, and they helped me, but they didn't know what I was doing. I mean, they just knew that here's this young kid who needs to cut 400 pounds of transformer steel, wind 22 miles of copper wire, and I did it on the high school football field.
How big was this Atom Smasher that you had?
Well, it was about this big, consumed 6 kilowatts of power. The capacitor bank was huge because it had to store the 6 kilowatts of power. And it gave us this tremendous crackling sound when I turned it on. The magnetic field was so powerful that in principle it would pull the fillings out of your teeth if you got too close to it. You had to be careful if there was a hammer or anything like that. In principle, if I ran it on DC, it would literally grab a hammer from across the room and fling it toward you. That happens at MRI machines today because they too have a magnetic field of about 10,000 Gauss. Now, today we have a big one, a real big one outside Geneva, Switzerland. That's huge. That's a Large Hadron Collider. That is basically my little machine scaled up to the size of a city. And that is the leading scientific instrument in the world today outside Geneva.
Why didn't we build it?
Well, we had designs for the Super Collider to be built outside Dallas, Texas in the 1990s. But then on the last day of hearings, costs were rising and Congress wanted to know should they keep on budgeting the Super Collider, and they canceled it. They gave us $1 billion to dig the hole, a second $1 billion to fill up the hole. That's $2 billion to dig a hole and fill it up. That's the wisdom of the United States Congress. $2 billion to dig and fill a hole. Now, why did they cancel it? In the last day of hearings, one congressman asked a physicist, quote, "Will we find God with your machine? If so, I will vote for it." So that physicist was paralyzed. Here was the question, are we going to find God with your machine? So he said something like, well, we'll find the Higgs boson. Well, you could hear all the jaws hit the floor of the United States Congress. $10 billion for another god darn subatomic particle. The vote was taken, and the next day, it was canceled. Since then, we physicists have spat our heads against the wall, wondering how should we have answered that question? Will we find God with this machine?
What would you have said?
I would have said this. I would have said God, about whatever signs or symbols you ascribe to the deity. This machine, the Super Collider, will take us as close as humanly possible to his greatest creation, Genesis. This is a Genesis machine. It will recreate on a microscopic scale the most glorious event in the history of the universe, its birth.
Did that turn out to be the same thing that happened in Switzerland?
That's right. That very same machine is now in Switzerland, and it found the Higgs boson. And we hope to find what is called dark matter, which is the next form of matter beyond ordinary matter. But our machine was canceled because we didn't know how to talk the language of the average taxpayer. That was a real lesson. We have to understand where the taxpayer is, because in the old days, we would go to Congress and say one word, Russia. Congress would then whip out their checkbook and say, how much? How much for the next atom smasher? Those days are gone. You can't do that anymore.
I want to show some video of you in 1997 saying some strong things about NASA.
I'm here to try to save the space program from NASA bureaucrats. NASA bureaucrats are trying to fabricate new laws of physics that I've never seen before in any of my textbooks, in any of the books that I have published for PhD students. In fact, if any of these engineers were to submit that report to me for a course, I would flunk them.
Why did you feel so strongly?
I believe in the space program, but I think we have to do it safely, because why will the taxpayers turn against the space program? When we lost the space shuttle, we came within a hair's breadth of losing the space program. The American people were saying enough is enough. 7 beautiful astronauts perishing because some bureaucrat authorized the launching of that missile. And NASA wanted to launch the Cassini mission, a great mission, by the way, which gave us gorgeous amounts of information about Saturn, with 72 pounds of plutonium. And this split the scientific community, because on one hand, we wanted Cassini to orbit Saturn, give us those great photographs. But on the other hand, if that rocket were to blow up, NASA's own computer program estimated that some of the plutonium could go to Disney World. Now, think about that for a moment. If you're a taxpayer and you realize that this rocket to Saturn all of a sudden caused the evacuation of Disney World, and you had to cancel your vacations and cross Orlando, Florida off the tourist map, you get really angry, right? And so I said to myself, it's not worth it. Chances are it'll be a success. Chances are we'll go to Saturn and get glorious photographs, which is what happened actually. But I said to myself, it's a gamble. Do we want to take that gamble and perhaps lose the space program? I love the space program so much that you have to save it from the NASA bureaucrats. And their attitude was, launch the sucker.
You say in your book that 544 humans have been in space, and that 18 of those have died. What do those numbers mean to you?
It means that 1% of the time, it's Russian roulette, 1% of the time you don't come back. 1% of the time. Now people ask me, would I want to go into space knowing that 1% of the time I'm not going to come back? You see, these people are test pilots. They are experienced astronauts. They go through the training, they take in courses. They know the odds. It's 1%. We're 60 years into the space age, and we have not got that number down below 1% misfire. In fact, to Mars, it's even worse, 30%. 30% of our space probes never reach it to Mars. And so, well, as Elon Musk said himself, he would love to be the first person on Mars, but he doesn't want to be there on impact. So I agree with that. We forget, space is not a Sunday picnic. 1% of the time, our rockets blow up.
Back in 2010, you were here on our program called In Depth, which is a 3-hour program. It's available, and the reason I mention it, it's available to our audience to go back and listen to 3 hours of you going into some detail on some of the things we're talking about. And it would be not a counter, but it would add information to people if they want to find out more of what you're thinking. Arthur C. Clarke, this is from 1964, and I want you to put him into context. A little bit of video.
What about the city of the day after tomorrow, say the year 2000? It will be possible in that age, perhaps only 50 years from now, for a man to conduct his business from Tahiti or Bali just as well as he could from London. I am perfectly serious when I suggest that one day we may have brain surgeons in Edinburgh operating on patients in New Zealand.
How's he doing on his predictions?
Well, he's right on the money. Now we have internet, we have telemedicine. Doctors in one place can do surgery using robots, in fact, even beyond what he said, handle robots, instruct the robots on the other side of the planet Earth. We have robots at Duke University that communicate with robots in Kyoto, for example, and different operations that you can do in Duke University, we can also do in Kyoto University. So if anything, I think he underestimated the power of the internet. And he mentioned, you know, being able to communicate anywhere on the planet Earth. Guess what? Elon Musk just last week unveiled a plan to create a planetary internet. Thousands of mini satellites, so that you're on the top of Mount Everest. And there you are downloading the Kardashians. And so today you have to have a microwave tower next to Mount Everest to do that. But if satellites, thousands of mini satellites orbit the Earth, then yeah, exactly what Arthur C. Clarke said could become a reality.
What does a theoretical physicist do when he has free time?
Well, for Einstein, it was like playing the violin. It was a time for him to think back at his work and to rethink his strategy. He also liked sailing, okay? Now, for me, well, I'm a professor, and I realized that I like to teach, but I can bore 20 kids teaching a course, but if I'm on radio or television, I could bore 20 million kids. So I said to myself, wow, that's an opportunity to touch the minds of young people. Because whenever I interview a Nobel Prize-winning scientist, I ask them, when was it that that spark of science began to germinate? And they always say, when I was 10. 10 is that magic year. You have that epiphany. You went to the planetarium. You saw your first telescope. You saw the moon for the first time in the rings of Saturn. You saw a microbe in a microscope. That epiphany stays with you for the rest of your life. So when you're an elderly scientist and you're tired and you have all these obligations, it's like a well. You draw water from that well continually over the decades because you remember that epiphany you had when you were 10 years old. And that keeps you going.
Do you play the violin?
No. Personally, I like to do figure skating.
How long have you done that?
Well, for the last 15 years. When I was a kid, I always liked to watch figure skating on TV, but to do something like that, that's rather complicated. But I realized as an adult that it's nothing but Newtonian physics. And if you are a physicist, you understand center of gravity, moment of inertia, you understand the basics of figure skating. So I said to myself, I can learn that. And so, yeah, if you see me spinning and jumping at Rockefeller Center, you know that it's me on the ice.
So if I were 19 years old and I wanted to see you in a classroom, for that matter, now my age, but if I wanted to, I'm starting out and I was interested, where would I find you? And why would I be in your classroom, and how large would that classroom be today?
Well, normally I teach to graduate students, and at that level, we're talking about a PhD program. You're only talking about maybe 5, 10 students, because these people are raring to go and they're doing PhD level work. But the university, the City University of New York, has so many young people at the freshman level, unwashed, raw students at the freshman level, that they said, look, you got to teach freshmen. So I decided to teach astronomy. And I was shocked. I looked at the astronomy final, and it was memorize all the moons of Saturn and memorize all the moons of Jupiter. That was the final exam. And I said to myself, I don't even know the moons of Saturn. I don't even know the moons of Jupiter. This is a worthless exam. You simply look it up in a book. I wanted to know planetary evolution, where stars come from, how they die, how they mature. So I threw out the curriculum, And they decided to import NASA videotapes about going to the planets and begin to talk about planetary evolution. Planets obey certain basic laws. They're born, they mature, and they die. You can teach these concepts because, as Einstein said, you can teach principles to children, especially pictorial principles. And so that's why I decided to take this small little astronomy course and make it modern. Now we're up to like 500 kids. The course is bursting at the seams because people have a thirst. If presented well, people will gravitate toward it. You know, when I first did television, people said that, quote, science doesn't sell on TV. But I said to myself, well, that can't be right, because 1 million people subscribe to Scientific American, another 1 million people subscribe to Discover magazine, and when there's a science special, well, you can actually get 5 million people to tune into that. So there's an untapped audience there. And then when cable took off, we found it. Yes, there really are 5 to 10 million people out there that will tune into a science program if, and only if, is presented well, with special effects, with a very cogent storytelling. People will gravitate toward it because we're born scientists. We're born wondering why the sun shines.
How often have you been involved in a television special?
Well, I work with BBC, Discovery Channel, the Science Channel, hosting specials for them sometimes, and of course Talking Heads. I regularly do Talking Heads for different science specials.
You do radio, and where can people find your radio shows, and how often?
Well, I'm on every week. They can go to my website, mkaku.org, or Facebook. We're up to 3 million fans on Facebook. On Twitter, we're up to 600,000 on Twitter. And they can find my radio schedule. The radio program airs in about 60 cities across the United States. And, you know, it's commercial radio. I mean, think about it for a moment. Commercial radio. We're not talking public radio. We're talking commercial radio, and the program is a big success. So it means that if presented well, people have a thirst, a real thirst to understand what's happening in the world, but it's never presented well. It's always presented as memorization, as learning stupid facts and figures you're going to forget the next day.
You talk about Ray Kurzweil in your book. Here is some video of him talking about life expectancy, and I want your input on this.
People say you take all these supplements and other pills, that's going to enable you to live hundreds of years, and the answer is no. That's just to get to Bridge 2, and Bridge 2 is not far away. According to my models, 10 to 15 years from now, we'll be adding more than a year every year to your remaining life expectancy.
Put Ray Kurzweil in the context, and he has a plan for himself, I think.
That's right.
How many pills do you take a day?
I think he takes several hundred. I talked to him once, and it's a considerable number. He also talks about 2 kinds of immortality. One is digital immortality, which is coming very fast, by the way. Silicon Valley companies are already offering a version of that now. And then there's biological immortality. Now, digital immortality takes everything known about you on the internet, your digital footprint, your credit card records, what movies you see, what wines you like to buy, what countries you visit, your videos, your pictures, your audio tapes, and creates a profile that's digitized which will last forever. So when you go to the library of the future, you will not take out a book about Winston Churchill. You'll talk to Winston Churchill. You'll talk to a hologram, and that hologram will have all the mannerisms, all the knowledge, anecdotes, story, everything known about Winston Churchill, and you'll talk to him. I wouldn't mind talking to Einstein. I would love to have an opportunity to talk to an Einstein based on everything that is known about the man. We could be digitized. There's a Silicon Valley company already offering to do this, and our great-great-great-great-great-great-granddaughter may want to find out who was their great-great-great-great-great-grandfather, because we've all been digitized. Now, to paraphrase Bill Clinton, is this really you? Well, it all depends on how you define you. If we define you as a biological entity, then this is a tape recorder, very sophisticated. But if you are the sum total of all your memories, emotions, feelings, if that is you, then yeah, in some sense, you could live forever because you've been digitized.
What is, I want your definition, please, for artificial intelligence.
Artificial intelligence is a machine that can do anything that a human can do. And let's be blunt about this. Right now, If you compare artificial intelligence to animals, our most advanced robot, Asimo, has the abilities of a cockroach, a retarded, lobotomized, slow cockroach. Our robots today can barely walk across the room. They can barely sweep the floor or turn a valve. But I foresee a time in the future when they'll be as smart as a mouse, being able to run around, find mates really quick, as smart as a rat, a rabbit, eventually as smart as a cat or a dog. But by the time they reach the level of a monkey, they could become dangerous. That's at the end of the century, I think, because monkeys have a self-awareness. They know they are not human. They know they're monkeys. Now, dogs are confused. You see, dogs think that we are the top dog, and they're the underdog, and we're part of the same dog tribe, the dog pack. So dogs are confused about who they are. But monkeys, they know they're not human. Once robots become as smart as monkeys, then I think we should put a chip in their brain to shut them off if they have murderous thoughts. But that's not for many decades to come.
Your own life, did you have brothers and sisters?
Yes. Mm-hmm.
How many?
I had one older brother and one younger brother.
And what did they end up doing?
Well, they're retired. My younger brother is a cardiologist, and he's still in private practice. And yeah, so we all went to college, and we all did what our parents dreamed of, and they wanted us to be successful.
What did your mother do? We talked about your father. What did she do?
Well, they passed away. My father was a gardener, and my mother was a maid. Because, you know, we were always strapped for money. I still remember my parents arguing about money and where should the money go, because, you know, we were flat broke during that period of time. And I still remember my mother talking about college. College is the key to everything. And I had this vision that college was this city in the sky. I still have that vision that there's a city in the sky called college, because that's the way my mother put it. And so now I realized that she was onto something, and that is, yes, college is a gateway to success in modern society.
How much of all of your education, and where did you get it all, was paid for in scholarships that you got?
That's right. I got accepted to Harvard, and also the Hearst Engineering Scholarship that Edward Teller founded. So I was the beneficiary of that. And then in my PhD program, there was money from the National Science Foundation. So luckily, even though struggling artists have a hard time scraping together their next meal, in sciences there is funding. The National Science Foundation, the Department of Energy will fund enterprising young PhD students. And so that, I think, is a good thing. You know, there's a brain drain into the United States because there is funding. Both private entrepreneurs, Silicon Valley billionaires will sponsor startups. And there is a National Science Foundation and the Department of Energy for more speculative and cutting-edge kinds of research. So there is a brain drain into the United States at the present time.
Go back to your 10-year-old example. By the way, do you have children?
Yes.
How many?
2.
And what kind of work are they in?
The older daughter is a brain doctor. She's a neurologist. And she's actually a professor now, a professor at Boston University.
And the other?
The other one followed a different road. She is a French pastry cook. She went to an exclusive school where they train and accredit French pastry cooks, and she's done very well in Manhattan.
Your mother said she wanted you to find a nice Japanese woman. Is that who you found for your wife?
My second wife is Japanese, and so my mother finally got her dream. However, I should point out that my mother eventually came down with Alzheimer's, and so it's very unfortunate that she could not even recognize me. Toward the very end, she could not even recognize herself. And so I thought that life in some sense is so unfair. You struggle so hard when you're young, and you're always poor, always wondering where the next check is going to come from, and then you lose your memories. You lose your sense of who you are, who your children are. You know, sometimes life can be very unfair.
What are you thinking at this age? Do I get it that you're 71?
Yeah. Mm-hmm.
I mean, what are you thinking about? How long are you going to teach, and what happens to the brain? You must know a lot about the brain as you get older.
Well, I realized that the body does, of course, decay, but the brain decays much slower. You could be sharp as a whistle, even in your old age. Einstein was publishing very important papers, even to the last days of his life. Now, when you get older, you say to yourself, do I want to write lots of papers that will get published, but are worthless? That you know they're nothing but dotting the I's and crossing the T's. I'd rather work on big problems now. Of course, there's a danger that nothing's going to come out of these big problems, but I would rather work on a big problem and fail than work on a lot of little problems and succeed.
From a standpoint of financial accomplishments, what categories have been the most lucrative for you? In other words, teaching, documentaries, radio programs, speaking, books.
Well, when I first started to write books, people told me you're never going to get rich writing a book because of the fact there's this cutthroat competition out there. And as Bill Clinton knows, you can make more money doing speaking at events and keynoting conferences and stuff like that. And that's something that I enjoy. It's something that I enjoy because you get to engage people and talk about things that are on their mind, things that are troubling them. And so I get invited to keynote conferences, for example.
Is that the best economically, the speaking?
Probably. And if you take a look at Bill Clinton and George W. Bush and people, they're on the circuit. In fact, I bump into them regularly. I've been on several programs speaking with Bill Clinton.
And how often do you teach your class with 500 kids in it?
Well, the university said, look, whenever I teach, whenever I have to go out and keynote a conference or something, I disrupt the university. I have to find a substitute teacher. I have to make sure that the grad students can grade the papers and stuff like that. Rather disruptive. And so they made a deal with me. They said, look, if we cut your slack so that you have more time for speaking and stuff, you can spread the good name of the university. The university benefits. You benefit because you don't have to run back to the college every time there's a speaking engagement. And that was a win-win situation. So they reduced my teaching load now, which is, I think, the ideal situation.
How big is your university?
It's one of the biggest on the planet Earth. The City University of New York has 250,000 students. It is huge. The State University of New York, of course, services the entire state. The City University of New York services, well, 8 million people altogether. That's the population of New York. Brooklyn alone would be the third largest city in the United States if you were to cut up New York City. So CUNY, the City University of New York, is gigantic. It is absolutely humongous.
Here's some, you read a lot about this in your book. You talk about going to Mars, and but here's a motion picture. Star Trek, 1979. It's not very long. I just want to show it and have you put the movies that we see in this country, again, in context with learning science. Have you seen all these movies?
Oh, I love them. I'm a science fiction junkie. So I watch all the Star Trek films and all the Star Trek stuff. When I was a kid, I just really loved, I gorged on the stuff. Today, however, I do a lot of cringing because I realize, oh, they got that law of physics wrong. Oh, they got that wrong. So a lot of times I have to suspend what I know about physics and just let my imagination roam, and that's the way to enjoy these films. So I love these films.
1951, the day the Earth stood still. Let's watch this one. Did you see this movie?
Yes, that movie was very important because up to then, the paradigm was War of the Worlds. The bad guys versus the good guys, we're the underdog, we're the good guys. That flipped it totally 180 degrees the other way. All of a sudden, we became the enemy. We were the enemy of ourselves. We're our worst enemy. And so that movie was incredibly important because it shifted the entire focus away from Martians invading the Earth to looking inward, to looking at our own problem. That if we explore outer space, if we mess up the Earth, we don't want to mess up Mars. We have to get our own act together. And so I thought that motion picture was pivotal because it shifted the center of gravity of science fiction.
What's specific? And this is book number 9 for you?
I think 14, I think.
Yeah, they listed 8 in the front part of it.
The other ones are PhD level textbooks.
But this one's called The Future of Humanity, and what was your goal in this book versus the others?
Well, the other is I talk about the future like 100, 200, 300 years in the future. But what's the pot of gold out there? What's the ultimate destiny of all these things? And so I said to myself, well, you know, as Carl Sagan once told me, we should become a two-planet species. We should join other civilizations in some kind of galactic civilization if it exists. And so, as people pointed out to me, the dinosaurs did not have a space program. And the destiny of the dinosaurs was to go extinct. That was their destiny. Our destiny is unwritten. But 99% of all life forms, their destiny is extinction. The norm for Mother Nature is extinction. If you dig right under our feet right now, you will see the bones of the 99.9% that no longer walk the surface of the earth. Now, we're different. We have self-awareness. We can see the future. We plot, we scheme, we plan. And so perhaps we're going to evade this conundrum and maybe survive, but we need an insurance policy. That's why this book is different from the other books, because the other books talk about the steps, but what is the goal? What's the pot of gold out there? And I'm saying is that one pot of gold would be to have an insurance policy, a plan B, in case a supervolcano, an asteroid, another ice age wipes out humanity on the earth or severely dents our history.
So this is 20 years from now. You'll be 91. You'll still be teaching and speaking. And you look back at what we've done in these 20 years, what will it be? And who will have been responsible for it?
Well, in some sense, my goal in life, that is what I want to do, is we physicists like to rank civilizations by energy, type 1, type 2, type 3. Type 1 is planetary, they control the weather. Type 2 is stellar, they control stars and play with stars, like Star Trek. Star Trek would be a type 2 civilization. Then there's type 3, galactic, they play with black holes, they roam the galactic space lanes, like Star Wars. Now, what are we on this scale? We are type 0. We get our energy from dead plants. But we can see that in 100 years, we will be type 1. But it's not guaranteed, because we still have all the savagery of our rise from the swamp just a few hundred years ago. We have the same sectarianism, fundamentalism, nationalism, all the backwardness of our rise from the swamp. But I see that by 2100, we will become a planetary civilization. And so I want to help speed up that process to make sure that we don't let the savagery of our rise from the swamp overwhelm our destiny, which is to become type 1. For example, what language will this type 1 civilization speak? Already on the internet, English and Mandarin Chinese are the two dominant languages. And the internet itself is the first type 1 technology that fell into our lap as we're still type 0. So we see the beginning of a type 1 planetary civilization, but we may not make it. Elon Musk just said that last month. Why don't the aliens visit us? There should be a lot of type 1 civilizations out there. They don't visit us perhaps because they didn't make the transition to type 1.
Do you have any idea why over the years, and it's been that case since I was even aware of it, that we refer to aliens as little green men that are going to land here someday? Why are they little green men?
Well, I think it's part of our subconscious, because Hollywood gives us these images as children, and as grown-ups we access these ancient memories of bug-eyed monsters, for example. By the way, I have some advice for people that claim to have met these aliens. Many people email me and say they've been abducted by aliens from outer space, so they know they're out there. My attitude is, the next time you're abducted by an alien, steal something. I don't care whether it's an alien paperweight, an alien chip, an alien pen. Steal something, because there's no law against stealing from an extraterrestrial. There's no law in the books that says you can't steal from an extraterrestrial.
What's your guess? Has there been extraterrestrials land on this planet?
You can't rule it out. I don't think so, but if you ask for hard evidence, there's no hard evidence either way. And so there is that possibility that in the past we might have been visited. It can't be ruled out.
Last video, you were alive, you were young, you were 8 to 10 years old. This is 1957, October the 4th. Somebody named Major John Glenn on a program called Name That Tune.
What do you think of the Russian satellite, which is circling the Earth at 18,000 miles per hour?
Well, to say the least, George, they're out of this world, but this is really quite an advancement for not only the Russians, but for international science. I think we all agree on that. It's the first time anybody has ever been able to get anything out that far in space and keep it there for any length of time. And this is probably the first step toward space travel or moon travel, something we'll probably run into maybe in Eddie's lifetime here at least.
Eddie, would you like to take a trip to the moon?
No, sir, I like it fine right here.
Major John Glenn was a test pilot then, and he had not gone to space. In your opinion, how have we done since 1957?
Well, I think NASA, unfortunately, became the agency to nowhere. It just spun wheels, went around the planet Earth. The space station was supposed to be the gateway for Mars and the planets, and that became a big turkey in outer space. So I think we've been basically spinning wheels for 50 years. But last month, just last month, there was this excitement, this electricity when the Falcon Heavy rocket blasted off, because that was a moon rocket, the first moon rocket in 50 years to blast off from Cape Canaveral. And guess who paid for it? Our taxpayers' money? No, a private individual, Elon Musk, paid for a moon rocket and basically gave it to the American people for free. This is unheard of. 5 years ago, 10 years ago, if you were to say that a private individual would create his own personal moon rocket and give it to the people of the world, people would think you were nuts. But it actually happened. So we're in a new ball game now. A new ball game where prices have been dropping dramatically, where the movie The Martian cost $100 million, but to go to Mars only costs $70 million. So Hollywood movies about Mars actually cost more than actually going to Mars. That's how cheap space travel has become. India, China. China's going to plant their flag on the moon. It's a national goal for the Chinese people. So things have changed. A sea change from the 1960s. Prices have dropped. Private entrepreneurs from Silicon Valley are funding a lot of this stuff, and China, India, everyone's jumping into the game. We're going to have a traffic jam around the moon.
Just got 30 seconds. What would you tell an 8-year-old today, watching you right now, and I'm sure they've seen you in the audiences when you speak, what should they do to prepare to become a theoretical physicist or a scientist?
Well, I tell them, keep that flame alive. That is, keep that spark, that inspiration, whatever it was that set you off in the direction. For me, it was trying to follow the works of Einstein, to complete Einstein's dream. Whatever it is, follow